Okay, so in this video we will take a look at more IP addressing, IPv4 that is, and this is from material from chapter 6. So we'll be looking at configuring IPv4 addresses, sort of our first look at subnetting. So to review, IPv4 addresses are 32-bit numbers divided into four 8-bit values or octets, and each octet has a value from 0 to 255. So this is just an easy way to look at these 32-bit numbers, which can be pretty massive. You can look at it as going from 0 to a little bit more than 4 billion, or if you look at it as signed numbers, they can be going from negative about 2 billion, a little bit more than 2 billion, to positive 2 billion roughly. And that's hard to look at. It's much easier to take this 32-bit number, divide it up into four groups of 8 bits, because 8 bits are a little easier to remember it, because each 8-bit value goes from 0 to 255. So this four decimal numbers separated by these dots is a format called a dotted decimal notation. Subnet masks are used with IPv4 addresses, and they are also 32-bit numbers that tell us how many bits are allocated to a network ID, and the rest are allocated to the host ID. So you have ones where the network ID is and zeros where the host ID is. So it's just a way of demarking, like in that 32-bit number, so many bits are network ID, correspond to the network ID part of the IPv4 address, and the other bits are allocated to the host ID part of that IPv4 address. So we looked at subnet masks earlier, and in this video we'll take a look at more subnet masks, but also we'll take a look at classless interdomain routing. So classless interdomain routing, or CIDR is how it's usually said. CIDR is the use of IP addresses without requiring a default subnet mask. And what you do is you just have to remember how many ones you have. So for example, 255, remember it's all ones, right? It's 8 ones, another set of 8 ones, another set of 8 ones, which would give us a total of 24 ones. So make sure you understand why it's 24. 888, 24, and then the rest are all zeros. So that's how subnet masks are set up. You have a certain number of ones. After that, it's all zeros. You cannot have ones and then a zero and then ones after that. It has to be, the left side has to be full of ones up to a certain point, whatever point you can decide, and then after that, all zeros. Okay, so the use of IP addresses with a default subnet mask is called classful addressing, as we saw in an earlier video. And the alternative to classful addressing is classless interdomain routing, or CIDR. And so there you just say that, well, if I want to represent a subnet mask like this, I would just put down the number, all of this, /24 for the 24 ones. So in this case, 172.31.210.0 would be the network ID, and if you have a .10 over here for an IPv4 address with /24, then the .10 would be the host ID part, and that's equivalent to having this subnet mask if you were to use a subnet mask. So once again, CIDR notation uses this format: some number dot another number dot another number dot another number /n, and that n is much smaller usually than, of course it can only go between 0 and 32. So it's a number of ones in the subnet mask. So for example, once again, 172.31.210.10, you can represent that IP address as having a default subnet mask of 255.255.255.0, or you can just say, well, this really just tells us that we have 24 ones, so you can write it in CIDR notation as 172.31.210.10/24. So the network ID is the first 24 bits, which are these three, and this leaves 8 bits for the host ID part. Okay, so within a local area network, you can have what's called a broadcast domain, which defines which devices in a network can receive a packet that's sent as a broadcast by any other device. So that's really important because we want to keep these broadcasts to as small a scope as possible. So broadcast, remember, is a packet addressed to all the computers on that network. So it has a destination MAC address, I guess it would be a frame, that would be all Fs. And we've used this in a number of protocols, most common being ARP, to find out the MAC address corresponding to the IP address that we know, and that's usually a broadcast in a local area network. And also something like DHCP. If you get a new machine on a network and you want to get an IP address for yourself, you send out a DHCP discover segment. So TCP/IP communication relies heavily on broadcast packets. These are examples. The thing about broadcast is that it's sent to everyone, which means you don't want to send it out beyond your local area network. You just want to send broadcast to a small number, as small a number as possible, but depending on your local area network. Okay, so subnetting allows us to do that, allows us to limit the size of your broadcast domain. It's a way of allocating bits from an IP address's host portion to the network portion. So I'm just going to give you a simple example. Oh yeah, so here's an example. Let's say you're given this range of IP addresses, 172.20.00, and so it's not obvious, but let's just say that the subnet mask is 255.255.0.0, which means that we have 16 bits that we can use to break it up into any number of subnets. And so typically we will try to find out, let's say given this big range of IP addresses, we'll say, well, we'll take a look at how many subnets you need, and to determine that you have to find out how many hosts you might have in each subnet and so on. There's a lot of things to consider, but that's the general idea. You're given some IP address, you want to divide. This is the host ID part. It's not obvious from here, but let's just say it is. And then you want to take that host ID part, 16 bits, and then break it up into subnets. Okay, so we'll see more details about this. Okay, so what you want to do once again is to take bits from the host part and convert that to network portions of your subnets. So thereby you create much smaller address spaces, and so you could say much smaller broadcast domains. So that's one of the reasons to actually subnet, to take a very large network which consists of many, maybe 65,000 hosts, and then if you have broadcasts in a network with roughly 65,000 hosts, that'll take up a lot of traffic. That will cause a lot of traffic jams, and so you want to limit the size of those broadcast domains. And so you take a very large network, divide it up into smaller networks where you can have smaller networks with smaller smaller broadcast domains. Another reason to do that is also for security. You want to take a very large network and break it up, and you want to divide up. You want to maybe install special networking devices like firewalls and special rules so that you don't get into certain subnets unless you have the right kinds of permissions, things like that. That's a good thing to do for any kind of network. So it's called segmenting or subnetting a large network. Another reason to do this might be to conserve IP addresses. You might want to use a range of addresses that are private IP addresses within certain subdomains. So it's a very common thing to do, is to take to like, if you take a look at the addresses in your home, chances are um, behind a DSL modem or a cable modem, your IP addresses are all actually private IP addresses that are not visible to the outside world. And dividing a network in small groups, there's a lot of benefits, like as we mentioned. You can get you can segment for security. You can also limit the size of each broadcast domain, but you end up with many smaller groups. Okay, so there is a procedure for calculating a subnet mask, and we'll go over many of these. And so let's say a typical task is you're given a large network and you have to figure out how to divide it up into smaller subnets. So first thing you might want to do is decide how many subnets you need, and each subnet will be behind a router interface. So each router interface connection will have a subnet attached to it. So then you want to decide, once you know how many subnets you need, you want to decide how many bits you need to meet or exceed the number of required subnets. So the problem is that we are going to have the number of subnets will be roughly a power of 2, and also the number of hosts in each subnet will be roughly a power of 2. It's not exact, but that's roughly the idea. So therefore we use this formula 2 to the n, in which n is the number of bits you must reallocate from the host ID part to the network ID. So remember, we are given a large network with maybe a large number of hosts, and so the host ID part might be, let's say, 16 or 20 or whatever, and we're going to take a few of those host ID bits and convert those to subnets. Thing is, since it's bits, it's always going to be a power of 2 roughly. So if you need, let's say, 60 subnets, you can't allocate exactly 60 subnets. You have to allocate the closest power of 2, and that would be 6 bits to get a total of 2 to the 6, or 64. So even if you only want 60, you have to set up 64 subnets. And you can't use 5, because if you said, well, 6 is too many because it's 64. If you use 5, you only get 32 subnets. So you can't use 5, you have to use 6. 6 is too much, but if you wanted 33 subnets, you still have to use 6 bits, unless you found a way to reduce the number of subnets that you actually need. But that's often not a possibility. You have a certain number of subnets that you want, in this case 60, and so in this case you have to use 6 bits and it's kind of unfortunate because you might not use all 64 subnets, you might only use 60, and so you can think of it as there being some loss or some waste in the number of bits, but that's, we have to live with that. Okay, so at that point you're ready. You're going to say that you have 6 bits from the host ID part that you're going to use to create subnets. You're reallocating the host ID bits, and you start from the most significant host bit, that is from the left side of the host ID. So try to remember that. You're allocating bits from the left hand side of the host ID part. It's easier to see when you see an example. You also have to make sure that you have enough host ID bits available to assign to computers on each subnet. So once you set up, you say that you have 64 or 60, I guess, subnets, and then you can figure out this formula, and it's slightly different. It's 2 to the n minus 2, and this will be a different n. And so if you take a look at the new number of host bits, which are the zeros in the subnet mask, and then take that new number, take 2 to the power of that, and then you subtract 2, and we'll go over why it's why we're subtracting 2. There's a specific reason for that. And so it's close to the power of 2, but not exactly. That's how many hosts that you can have. And maybe it might be possible because of, because you didn't foresee that it's not enough. That's always a possibility. But you cannot change that. You have to change the entire subnetting procedure to somehow accommodate more hosts than you are capable of having. So here's an example. This is a pretty good example. So you're given this network 172.20.0.0, and let's just assume that the subnet mask is 255.255.0.0, or you can say 172.20/00/16. So if you want to break it up into 64 subnets, so the way to look at this is, if you use this technique, this is what you end up with. The first subnet will be 172.20.0.0, same as the original, but then the next subnet will be 172.20.4.0, and the next one is 8.0, 12.0, and if you count all of these going up by 4 each time, you will see that you will end up with 64 subnets. You can take a look at the bits of that third octet from the left, and so here it is. I don't know if you can read this, but that third octet is 170. So I'll read the whole thing. 172.20. And it's in binary here, so it's kind of odd, but we usually don't do this. The book does it, and it's sort of good, but it's kind of odd to see right in the middle of these decimal numbers a binary number. And the book does it just so that you can see the pattern. So 172.20.0.0 is 172.20. And then 8 zeros, .0. The next one is 4, and so you'll see 1, 2, 3, 4 zeros, and then a 0, 1, 0, 0, which is binary for 4. And the next one is 0, 0, 0, 0 dot, sorry, 0, 0, 0, 0, 1, 0, 0, 0, which is 8. The next one is 0, 0, 0, 0, 1, 1, 0, 0, that's 12, and you can see the pattern now. 16, 20, 24, 28, 32, which is 0, 0, 1, 0, followed by 4 zeros. That's 32. So take a look at this. Just make sense. I mean, just make sure that it all makes sense. And there's 2 sets of values. You see the decimal part and the corresponding binary part, but the binary part is only shown for that third octet from the left, because that's where we're doing the subnetting. Okay, so what we're saying is, here is the first subnet, and there's a range of host addresses that you can have, and then there's the second subnet. You'll have the same size of the range for that subnet, and so on. So here is a look at the range of host IDs that you can have. Let's say the first subnet is 172.20.0.0, and so we're saying that we're going to have 1, 2, 3, 4, 5, 6 zeros for the subnet, and then the rest, that is 10 bits, can be used for the host ID part. So make sure that makes sense, and you can see the pattern here, because I'll read it out. It says 172 in, so let me back up here. It's the subnet IPv4 part is 172.20.0.0. We will fix the leftmost 6 binary bits to be all zeros, and the rest can vary. It can go from roughly 10 zeros, except for the last bit is 1, to roughly 10 ones, except the last bit is 0. And if you write it out, this is what it looks like. Here are the beginning and ending host addresses: 172.20.0.1 to 172.20.3.0.0. 172.20.254. So these numbers are important, and here's why we're not using 172.20.0.0. That is actually our network ID. So we cannot use that as a host ID. So that's why the beginning host address is 172.20.0.1. We cannot use the 0 there, and that's why if you look in the binary representation, there's 10 zeros, except the very last bit is not a 0, it's a 1. And then at the other extreme, it's almost all ones, except the last bit is a 0, because all ones would be the broadcast address for that local area network. For that subnet, if you had all ones here, that means do a broadcast. So we cannot use the 1 in the last bit. That's why we end up with, in this case, 172.23.254. And that's the pattern you'll see throughout. The next subnet is 172.24.0, and you can see that it'll be 5 zeros and then a 1, because the 00 after that will be 4. That's our network ID. And remember, you cannot have all zeros after that, because all zeros is actually corresponds to the subnet ID, and you cannot use that. So you have to start with the 1 and then go all the way to almost all ones, except the last bit is a 0, because that all ones case would be a broadcast address. So you might have to think through this, look at this for a little bit. I think eventually it'll make sense. We'll use this quite a bit. And so once again, you cannot, there are certain host IDs that you just cannot use. It looks like it would be valid host ID, but it's not, and that is really why we end up with this 2 to the n minus 2. All zeros not allowed, because that's the network ID part. All ones not allowed, and those two things not being allowed is why you subtract 2 from 2 to the n. Okay, so there is a method to all of this, and I'm hoping it doesn't put you off too much. So here's another subnet mask example. Let's say you're given a network ID 192.168.100.0, and you have to break it up into little subnets. So you have routers. Routers naturally break up a large network into smaller subnets, and then you have to make sure, like in this subnet A, you have 40 windows, 10 hosts, plus a server and another server. So basically 42 machines. You just have to make sure that you have enough host ID bits when you do the subnetting to accommodate 42 machines here. In here it is 52 hosts, that is 50 hosts plus 2 servers with 2 switches, but that doesn't, it doesn't matter. And then over here it's 42 machines in this subnet. So if you look at the closest power of 2 for all of these, it'd be 40 here, 52. So 52 is the largest. Chances are you'll have to go to 64, which is the closest power of 2, but remember, you subtract 2 from 64 to give you a total of 62 hosts in each subnet. Okay, so that's doable given this IP address range. Another thing too, I just want to back up and just have you notice this one special thing, is that anytime you have a router to a router connection, that is actually a complete subnet. You may not use all of the addresses. You may only use 2 addresses out of this subnet, but you have to subnet it. You have to give a router to router connection. You have to make it a separate subnet. So in this case, although you only really have 3 LANs, because of this rule about connecting routers, you actually end up with 4 subnets, with one subnet having just 2 addresses, others having 42, 52, and 42 hosts. So seems like a waste, but that's just how things work. You have to have a subnet that is capable of having, let's say, 62 hosts, but only has 2. Okay. So if you take a look at needed host addresses, this is a good example. So let's say we're taking a look at 3 different classes of networks. So if you have a network ID of 10.19.32.0 and you need 900 hosts, remember the closest power of 2 would be something like 2 to the 10, which is 1024, which means that you have to use 10 bits for the host ID part, which means you're left with 22 bits for the network ID part. And remember, even though the host ID bits is 10, which gives you 1024 possibilities, remember 2 of them are gone because of network ID part and broadcast part, so which basically gives us something close, 1022 hosts maximum, but that's enough to fit the required number of 900 hosts. Similarly, if you have a IP address range like this, 172.25.110.0, and you need to have 505 hosts, the nearest power of 2 is 512 with 9 bits, but then remember 2 of those you cannot use, so you end up with 510, which is good enough. 510 is bigger than 505, and so you can use 9 bits and accommodate the required number of hosts. So using 9 bits for the host ID part leaves you with 23 bits for the network ID part. And so in CIDR notation, this would be, you will write this as 172.25.110.0/23 for 23 network ID bits. Let's say we have another subnet 192.168.100.32 and we need 28 hosts. Nearest power of 2 is 32, so which means 5 bits. And remember, you lose 2 of those, we end up having only 32 hosts possible, but that's good enough to fit 28, and so we go ahead and use the 5 bits for the host ID part, which leaves us with 27 bits for the network ID part. And so we would write the address as this way in CIDR notation: 192.168.132/27 for 27 network ID bits. Okay, so that's a quick look at subnetting. Let's also take a look, very brief look at supernetting, which is something that we won't really do a whole lot of. Supernetting is needed usually at the routing level. It's sometimes necessary to solve certain network configuration problems, just to make our routing tables a little bit easier to set up, easier to follow. This is also referred to as route aggregation or route summarization. We're taking a bunch of smaller subnets and combining that into a larger supernet. So supernetting reallocates bits from the network portion of the IP address, so subnet portion, to the host portion. So it's opposite of subnetting. Essentially what that does is take 2 or more smaller subnets, combines them into a larger supernet. So we don't really physically make a larger network. What we do is, let's say we have a router connected to 4 subnets, and these are pretty close, like 192.168.0.0/24, 192.168.1.0/24, 192.168.2.0/24, and 192.168.3.0/24. So let's say we have just these 4, and we don't have, so we would have a routing table that says 192.168.0.0/24 is connected to Ethernet A, which let's say is over here, and Ethernet B is connected to the next one, Ethernet C of the router is connected to the next one, Ethernet D is connected to 192.168.3.0/24, these 4 subnets. And let's say we're not using some of the others, like 192.168.4.5.6, none of those are, let's say, in use. In that case, we can say, well, here's a way to simplify your routing table. If you have anything from 192.168.0.0/22, that is 22 bits of ones, then send everything in that range of addresses to this WAN A interface of this router. So on this side of the network, you're taking, basically considering all of these four networks, subnets, as one big network, and that's on the WAN A side, the WAN A interface of this router. Okay, so we'll see more about routing and things like that later, but this is just a preview. It just shows you one way of simplifying a routing table. Instead of having 4 entries now, you just end up with 1 entry, and that'll work assuming certain things about your subnets. And in this case, it's perfect. There's no problems at all. Okay, so remember the rules for IP address assignment. A host can be assigned only a Class A, Class B, or Class C address if you want to route to it. Every IP address configuration must have a subnet mask. You can also use CIDR notation. All hosts on the same physical network must share the same network ID in their IP address. All host IDs on the network must be unique. You cannot have 2 hosts with the same host ID. That's just, it's possible, but it's going to be messed up. It actually is possible, but a lot of operating systems will detect that and complain and say you have a bad configuration. You cannot assign an IP address in which all the host ID bits are binary 0, because remember, that is the network ID or subnet ID. Similarly, you cannot assign an IP address in which all the host ID bits are binary 1s, because that is the broadcast IP address. So all 0s not allowed, all 1s not allowed. Okay, so remember that. And computers are assigned different network ID that are assigned different network IDs can communicate only if a router is present to forward the packets. So if you have 2 different networks, you have to have a router connecting them, if you want to connect them. The default gateway address assigned to a computer must have the same network ID as that computer. Okay, so you cannot have a default gateway address outside your network. It has to be inside your network. It's usually the router port. That is the default gateway. Okay.